So someone asked a question about short circuits, and so I wanted to follow up on what we talked about in class and try to give maybe a better picture of how a short circuit works. And so let's look at a situation where we have two parallel resistors, one capital R and one little r. And let's say that our battery is delivering a current right now of I total. And so we want to look at how does this current split up between these two resistors. So the place we would start first is to find the equivalent resistance. And so this is we did this in class, but I'll do it again. So 1 over R equivalent equals 1 over little r plus 1 over big R, since these are two resistors in parallel. And the fastest way to solve for this is to make a common denominator. So I'll make big R over R big R plus little r over R big R. And when I add those together, I'll get R plus R divided by RR. And by flipping that over, I get R equivalent comes out to be R big R divided by R plus R. So that's the equivalent resistance of both of these together. And so what we can do now is figure out what is our total voltage drop across this piece here. And so our voltage drop for resistors is just I times R. And so in this case it would be my I total by my R equivalent, which I'll write in this thing here. And so, assuming that this current is I total and that my resistors are big R and little r, this is the change in voltage across both of these resistors. And so now what is convenient to do is to figure out, well, what is the actual current across each one? So for instance, the current across I big R, I would use this voltage drop, because remember, our Ohm's law says I is equal to V divided by R. And so in this case here, just the current just across R, the big R, would be this I total R big R divided by this. So it's kind of ugly now, but we'll see in a second it's going to clean up. And then this one would just be divided by big R. And so that big R will cancel with the big R up here, and we get an equation that we're going to see is a little bit easier to manage. So it's the total current times R over R plus big R. And if I do the same thing for little r, okay, I'll get a really similar equation. So I get this I total. Again, it's the same voltage drop because the resistors in parallel have the same voltage drop, and to find the current, I take that voltage drop and divide by the resistance. And again, I get these r's to cancel. This time it's the little r that cancels, and so I get I total big R over R plus R. So make sure you follow all this before we go to the next part. In the next part, we kind of explain it a little bit more about how this stuff works. So now we've got our two equations for the current, so how the current splits up. And you can check this, all right, just like our current always works. This will work out that I total will equal I big R plus I little r. You can check that out, and that totally works. But we want to know is a little bit more about how this works in different cases, especially the case of a short circuit. So the first thing that I can do is let's just do a simpler example and say let's just do, that R is maybe 10 ohms and little r is 5 ohms. Okay, so what does that lead us to here? Well, if you go through and do this, my current across big R would be whatever that total current is, and here it's R over R plus R. And so what would I get? I would get something like this. I'd get my 5 ohms over 15 ohms. And we should be real careful. These are ohms. My R's and my ohms can kind of meld together. But in the end, what I get is I get I total over 3. And if we do the same thing for I little r, we get I total 5. And this time, when I plug in, so it's over here, so I get 10 over the 2 r's added together, or 15. And I get I total times 2/3. So again, like we said over here, right? It adds up. We have a third of the current and then 2/3, and so together that's the full current. And so how does it split up? Well, it splits up so that more current goes through the less resistance, which is kind of what we know qualitatively. But we can go through here and show that quantitatively with the numbers right here. And that's how it always works. And so you can always, sort of take this with any resistance combination you want, and it'll work out the same way. The more current will go through the smaller resistance, but it's not like it's that much more. Okay, so it's like 2/3 here and 1/3 here, so it's not like a crazy amount. And so now what we want to do is look at the really extreme case where R is much, much less than big R. And that's the case we're looking at, which is the case of a short circuit. And if you want to stop here and actually do this yourself before we move on, that would be good. But what we can do then is just take those same equations, right, these two equations over here, and just do that for the case where R is much, much less. And what's going to happen is in that extreme case, okay, what we're going to find is that the bottom part of that fraction, you can just neglect that R. And so for I of R, it's going to be I total R over big R. And in this case over here, all right, we can again neglect the little r because it's just so tiny that adding it to that big R makes no difference. And I get R over R. Okay, I should say that these are both approximate cases, for the situation when R is much, much less than big R. And if you get R divided by R, that just equals I total. And so again, if we sort of write this out down here, for I big R, we approximately get I total times R over big R. And for I little r, we get approximately I total R over R, or just I total. And so this is what we're saying with a short circuit. With a short circuit, when this happens, when the R is much, much less than R, okay, the current going through this one is approximately all the current. Now, depending on how you pick these numbers, it's not going to be exactly all the current, but it's going to be pretty much, 99.999% or something like that. And then over here, if your R is truly if your little r is truly much, much less than your big R, then this essentially comes out to be 0. All right, and so if you can kind of make sense of this case here, where we just sort of have more, one is bigger than the other, you can kind of sense how one goes, the more current goes to the smaller one. Then in the extreme case, you can make an argument that all the current will go through the smaller one and completely bypass the bigger one.